So this was the slide we left on. Now, this is apparently one of the largest impact basins. It's hard to get scale. If you're like me, when you look at the moon, it's really hard to get scale. From what will I know about scale, you cannot see the flag on the moon. I know that. So I've got some sources over here. I'm not real sold on Google Moon, but there are a couple other links. Like this is a zoomable map, just like it says. And what I don't like about this map is that it's zoomable, which is great, but they don't have it doesn't say what those things are. Starts with the letter T. What's that big, humongous one with a big ejecta blanket? Tycho. Yep, that's Tycho. Like Tycho Brahe? Okay. So that's a good one. And to kind of supplement that with this one, I like this one. This one has the name, so I'll go ahead and post those out there on Canvas so you can see it. The way this one works is if you hover over an area, like you guys told me that's Tycho, and you're right. So that's kind of how that works. The dark region starts with the letter M. What are they called? Mare. Yep. And yeah. So it's cool. Can you see the face of the man in the moon? I don't know. I have a hard time seeing the face of the man in the moon. So, a lot of digital resources out there. I feel like these next two slides, we've already kind of talked about some of these features. Like, we already talked about that. So, for instance, we talked about ejecta blanket. Tycho has a big ejecta blanket. The lighter the color, like Tycho's stuff around it is so light, that means it's relatively recent. We talked about, I call these central peaks, I call those belly buttons, okay? Central peaks in the middle of craters, and then the terracing happens. All right. You guys told me Mare are the dark areas. Starts with letter H. What are the light areas? Highlands. Very good. Yep. Highlands. So if we were to look at the whole moon, this has been my moon. This says near side, this says far side. If we look at the whole moon is about, 83% of it has the highlands. Okay, and we already kind of talked about it. So what does that mean about the mare? Which side has more mare? The near side or the far side? The near side has a lot more mare. Yep, not much mare over there. Another map. You guys told me Tycho. And like I said, on my list of things to do, I'm not really good about pointing at the moon and saying, well, that's the Copernicus crater, But maybe when I retire. Here's a couple of pictures of the moon. What phase is this, you guys? Is it a crescent or a gibbous? Gibbous. It is a gibbous. Do you think it's waxing? Or how many people think it's waxing? I do too. Why do you think it's waxing? Yes, because whatever's happening on the left is continuing. So it's going to keep getting more and more illuminated. It's waxing gibbous. Very good. What do you think that phase is? Full. Very good. What sort of an eclipse can you have, lunar or solar, when it's a full lunar eclipse? Yep. You're just firing those off. I just have some pictures to kind of show you. This is kind of showing you, isn't this beautiful? So the sun's over here, and this ridge is casting a shadow back there. Just beautiful. Again, kind of the shadowy areas. This is a good picture if you see the belly button, the central peak, and you can kind of see some terracing. Get a little sense for the pulverization of the, starts with letter R. What do we call that stuff? The pulverized rock. Regolith. Yep. This is kind of a hill on the moon. Actually, Dave Scott in one of the groups I play in is a percussionist. His name is Dave Scott, but it's not the Dave Scott. I think that's kind of funny. Another picture of the moon. It's gorgeous. So the series of Apollo missions have gone to the moon with a variety of success. I think it's interesting that one of the things that spurred us to go to the moon actually was our competition with Russia. It was also a military thing. Including Tang, there's been lots of things that have been discovered or developed for the moon missions that have been used here on Earth. So here's a picture of Dave next to a big old rock. Wait, no, this isn't Dave. This is, oh, sorry. Sorry, Senator. The next picture I'm going to show you is a picture of some moon rocks. Here, actually, this person is carefully looking at, inspecting a rock that came back from the moon. What a rush. So one of the things, if you're into kind of the Star Trek sort of, you know, it's thou shalt do no harm to the places you visit, and we like took back rocks. Now that should be done, but we did. We took back rocks. They kind of fall into three categories. The Mare rock actually are kind of like lava. If you've kind of seen rocks from the Hawaiian Islands, that's kind of what it looks like. Northocite are from the highlands on the moon, and they're kind of like our mountains. And then we have these impact breccias, which we don't really have here on Earth, and the word kind of gives it away. These were created kind of, they're sort of a fused sort of deal as the moon was bombarded by meteors in its early history to kind of create these rocks. Three rocks. This is a close look at one of the basalt rocks. So mascons, and I tried to find, mascons is a kind of a concept that I was familiar with, and some of these newer astronomy textbooks don't necessarily include it, but has gravity, right? Has gravity. So actually you can get a sense for the gravity as you orbit. We have orbited the moon. So there is a place in the moon where basically there's more gravitational pull. And that's probably because it's just got a dense rock there, dense material. And it's lopsided, it's not homogeneous. Okay. Do you think there's water on the moon? How many people think there's water on the moon? There is, there's all sorts of. There's definitely water on the moon, a lot encampments at the polar areas. So do you think there's life on the moon? No. There's not been life found on the moon yet. So. Yet. I don't think they have it, but I don't know. So these will be due when we come back on Friday, Fabulous Friday, the equinox. So now we're going to go ahead and switch gears a little bit, and we're going to talk about the last part. The last part, as I was getting ready for it, I'm like, man, there's a lot of slides, but there's a lot of pictures too. So we'll see what you think. When I was trying to decide how I wanted to teach this material this semester, I ended up, I thought about trying to talk about the formation of our solar system before I talked about this, but that's okay. So what's this? It is the sun. Very good. Okay. And I've talked a little bit about, I've alluded to this idea of how did our sun and the planets form a little bit. Oh yeah, remember when we talked about, I don't know if I can put this in the form of a question on your test, we talked about potential energy and kinetic energy. So we talked about throwing the ball up. If you throw the ball up, and right here before it starts to fall, does it have a lot of potential energy, a lot of kinetic energy? Potential. A lot of potential energy. And then right before it splats on the surface, so it didn't stop moving yet, does it have a lot of potential energy or kinetic energy? Kinetic, yeah. So I mentioned this because then I changed gears and I went to this. This is my nebula, okay? And there's different ways to get a nebula. The nebula we saw last night, the Ring Nebula, M57, that Ring Nebula is a lot smaller than the nebula, well, that I'm probably going to talk about. That particular nebula is called a planetary nebula. It has nothing to do with planets. But that nebula is created, I think I talked about a star kind of is ejecting its material. But this is a bigger nebula. And so what happens when it's nice and big? Does it have a lot of potential energy or kinetic energy? Remember? Nice and big. And I'll make it small here in a minute. Oh. It has a lot of potential energy if it's like this. Yep. And so as I make it smaller and smaller and smaller, does it have more potential energy or kinetic energy? More kinetic energy, yep. And actually, kinetic energy can translate to high temperatures. If you have a lot of kinetic energy, do you have high temperatures or low temperatures? You have high temperatures. And that's kind of at the crux of how stars get born. They have to create enough temperature and pressure actually in the core to begin taking hydrogen and ramming them together at high temperatures and pressures and making helium out of them and releasing a little bit of energy. So anyway, so that's how that goes. Very good. So picture that process about 4.6 billion years ago. Okay, and that sort of nebula we're going to call the solar nebula when we talk about it. But anyway, as that happened, the sun did its thing. The sun got enough high temperatures and high pressure to begin nuclear fusion in its core. But there was extra stuff on the edges, and that stuff, it's kind of like a snow. Who in here has ever made a snowball? Right. So it's kind of like making a snowball with the planets, okay? So that makes the sun, the star, and then what's kind of leftovers makes planets. Now that brings us to this idea of not everything got turned into a planet, and that's kind of our leftovers. It's our crumblies, okay? And they fall into a couple broad categories. There are the rocky stuff, and we're going to start with that didn't turn into a planet. They're called asteroids and meteoroids. The only difference between asteroid and meteoroid, they're rocky, and I will tell you size. These are bigger. Oops, yeah. These are bigger, that's it. And these are smaller. Okay? And the cool thing is, or there's lots of cool things, well, there's some dangerous things too, right? But a cool thing is that actually, as they exist in outer space doing their asteroid or meteoroid thing, okay, they have been that way ever since about 4.6 billion years ago when the sun turned on. When the sun turned on, it kind of cleared the extra gases, and the rocky stuff kind of stayed behind. Of course, the planets stayed behind. Okay, planets were forming as the sun. So I wish I didn't have this picture here because this is neither an asteroid or meteoroid. First letter C, so what is this? It's a comet. And actually, we're going to talk about comets in the next part, but if that's the sun, comets are way out here, okay? So the difference is they get out here, not only are they rocky, but they literally have like ice. They have an icy component to them. So comets are like out here. Now, comets out here don't look like that. I'm kind of getting ahead of myself. But comets only that kind of get a nudge and come close enough to the sun, they start to fizz like an Alka-Seltzer tablet, okay? And in that fizzing, that's actually when they see this like this. If the comet's out there like that, icy body does not fizz. It's close enough to the sun and it fizzes and it will orbit the sun and then it will go back out here. Sometimes it takes like, hundreds of thousands of years to complete one orbit for a comet. But back to the rocky ones. Okay, asteroids. So they're kind of leftovers, the beginning of the solar system. So I've got some slides to kind of show you some pictures of asteroids. So which are bigger, asteroids or meteoroids? Asteroids are bigger, yep. Got some cool close-up pictures of asteroids. Can you kind of see the little pock marks? It's like they have been hit by, they have little craters, okay? Most of them are kind of odd shaped. Now the reason, by the way, when we talk about Mars, I'm telling you, Mars's moon kind of looks like this. It's like one of these random. Mars has 2 moons. Totally not like that. The reason that they didn't get kind of the nice spherical shape is there wasn't enough mass to kind of, for gravity to form them into a sphere. So they're on the light side. Now, we have a couple kind of spherical looking ones. Is this the same one? Got Vesta, okay, and Sirius. So this is Vesta. Now, we're going to talk about where these rocky bodies are. Where are these asteroids, meteoroids? And some of them are located, okay, what comes Mars? What comes after Mars? Jupiter, yep. Some of these asteroids are actually located in the asteroid belt you probably heard about, between our last terrestrial planet and our first gas giant, or Jove planet. Sirius and Vesta are there. And you can kind of see the spherical shape to these, because actually these objects were big enough to go ahead and the mass and gravity to go ahead and round them over. So now, as I'm talking about Sirius and Vesta, who are here in the asteroid belt, let me talk about Pluto just briefly. Is Pluto a planet anymore? No. Pluto is a dwarf planet. I mention that because so is Sirius and Vesta. Sirius and Vesta are dwarf planets, and so is Pluto. In other words, if they had their act together when they were naming planets,
It'd still be planets.
maybe if they had gone ahead and named, these objects in the asteroid belt as planets, we never would have had this heartbreak we've had. So asteroids. We see asteroids. Asteroids don't glow. They do not glow because they have no nuclear fusion. So we see asteroids the same way we see the moon, which is sunlight. So we can actually see, and it's on my list of things to do. I've had some friends at observatory do it. But if you see an asteroid in the nighttime sky, it's going to be just like a pinpoint of light. And I think I got this right. Yeah. I think that this is a time-lapse photo. I don't think that you really see asteroids streak. This streak right here is supposed to be an asteroid. I think like if you plot it now, you plot it later, it's going to move against the background stars. All right, asteroid. Actually, no, asteroid, sorry. Well, this is showing another term we're going to focus on, or try to make sure we're all on the same page is, you guys told me meteoroids are smaller than asteroids, right? But meteoroids and asteroids are both space objects, rocks. A meteorite is something that actually the rock came from space and it hit the Earth. So I'm hoping you will, when you leave this class, know that a meteorite is something you pick up from the Earth, and a meteoroid is something that's still out there. We have one third term called a meteor. It's coming here. Okay. So this is actually meteorite, an object that fell on the Earth, and we picked it up and said it's a space rock. Now, I've done a little bit of dabbling, kind of looking, how do we know this is a space rock? And you feel free to kind of check it out yourself, but it's about rock chemistry, basically, to identify it as being non-terrestrial. Can you guys hear me okay? I think he enjoys that. Okay, now these are back. We're back in outer space again. Here we have Matilda, Gaspra, and the meteoroid or asteroid Ida. Okay, this is talking about, This is...
What's the difference with the S-type and the C-type?
I'm not sure. I would have to look that up too, S-type and C-type.
Okay.
Yeah.
I didn't know, I just asked.
Yeah, it might have to do with, I'm recalling maybe density, like one is more dense. And have you heard, kind of related to that, that people have started to look if they can mine these things, go out there and bring them in or land on them and, for their minerals. So it's an interesting idea. This is Ida and Dactyl. Actually, Ida has its own little moon. Dactyl is its moon. Can you see that? Isn't that cool? This is another asteroid, Eros. Another asteroid, it's Ikawa. See what I mean? Just like a little picture of it. So this is back to Sirius again. A, Vesta, B, Sirius. So this is Vesta and Sirius. The next slide actually is going to kind of hone in on this little white spot right here in Sirius. There have been numerous interactions with NASA sending spacecraft out to these asteroids. And Sirius and Vesta have been visited by, I can't remember which one. But this is a close-up of kind of this bright region on Sirius. There you go. Okay, so where are those leftovers? Where are those asteroids? So you guys told me Mars and Jupiter, so you can kind of see Mars and Jupiter on there. I don't like this slide in a sense. Those are the orbits of those two planets. This actually is kind of propagating the misconception that if you are in the asteroid belt that the little asteroids are very close together. They are not. Okay. But where you find asteroids, that's one location. Now notice sometimes students say, well, is it just a failed planet? If you were to take all that stuff, scoop it up and make it into a planet, would it be enough to make a planet? The answer is no. So there are 3 places. That's one place. One place right there. Another place, it's kind of subtle. I don't know, let's see how it's looking here. But can you kind of see this right here and this right here, and there's Jupiter. That's the second type of asteroids. They're called Trojan asteroids. So as Jupiter moves, the asteroids in front of it moves, and the asteroids behind it moves too. So they escort Jupiter around. They're at these stable, like Lagrange points. So yeah. The other day we looked at an image from a spacecraft associated with our planet that, remember, it got on, where's my moon? Here's the other side. Remember we looked at a picture of the satellite was here, it looked at the moon, and then it looked at the Earth kind of together. And it was called an L location, a Lagrange place. It's just like a sweet sort of place for it. Actually, as I understand it, as far as Trojan asteroids go, Jupiter has them and the Earth has them too. But they'll never catch up with the planet. It's just a gravity thing. The third one are the Apollo asteroids. And if you're into like worrying about getting hit by an asteroid, that's going to be them. I can't really draw Apollo asteroids. Let's see. Mars, we're next to Mars, we're the blue one. So an Apollo asteroid would be, for instance, one that just kind of is a wild child and it kind of goes like this. How about I just kind of draw one like that? That circle, if that was the orbit of an asteroid orbiting the sun, can you see where it crosses Earth's orbit? That's an Apollo. So it's the Apollos that we're most worried about. So one thing about that, Jupiter is the largest planet, and it's got the most gravity, the most mass, and it actually, over time, I think this is one of my last slides, I guess, coming up. Over time, it has been that can't be Jupiter, it's the moon. If I change this into Jupiter, it's done a lot of deflecting for us. And actually, it's created these gaps also in the asteroid belt. And here's where it says, although asteroids are spaced far apart, oh, sometimes they do run into each other, but they are very far apart. All right, so this is a closer look. You can kind of see that itchy looking thing is the asteroid belt. And you can kind of see the Trojan asteroids. They're here in green, escorting Jupiter around. Okay. So here's the 3 M terms that I want you to get under your belts. And to me, the oid thing kind of gives it away, because I remember asteroid is out in outer space, and so is a meteoroid is also in outer space. It's just smaller. What's the size break? I don't know. So then aside from that, our other M, if you're kind of going in order, potentially, is meteoroids, and asteroids and comets actually, Meteoroids can, at times, be drawn by the Earth's gravity to fall to the Earth. And as they do that, they're going to fall through the Earth's atmosphere. And as they fall through the Earth's atmosphere, they are going to glow. And we saw a few of those last night. Okay, that's what we call a falling star, a shooting star. Yep, that will glow. And depending on how much of there was, how big the meteoroid was, sometimes it entirely burns up. More likely, though, I suppose, there's some of it left and it lands on Earth. And if that's the case, it's the third M, it's a meteorite. Pick it up. There's 3 M's. So that is a big meteorite. This one right here. Again, you're like, well, how do they know that? And read up on it if you want, but it definitely is not terrestrial. I don't know, I'd be scared to have my kid touch it. I'm just saying, I'm sure it's okay. Cool. What's that?
They'll turn into maniacs.
Right. Oh. What's that?
My super ex-girlfriend, it's a movie, she touched an asteroid rock and she got superpowers.
She did? Oh, see? I'm just saying.
It happens.
It happens.
Then I would touch one just in the hopes, right?
It was like
But they can be worth a lot of money. So here's the streak. What do we call this streak? What do they call it, the streak? What? The meteor. Yeah, that's the meteor. Yep, that's the streak. Yep. Now these are, we'll be talking more about telescopes. These actually are not visual telescopes. These are radio telescopes. Big. Okay, this is the same meteorite. And you can see they like put their children in it. I don't know. So, a good place to look for meteorites are at the poles. Why do you think that is? Probably a couple reasons. They're drawn there. Magnetic
Field pulls it there.
I can see that. How is it easier to see them? Did I hear someone say the snow? Yeah. And the other thing is they don't have a lot of, aside from polar bears maybe, I mean a lot of foot traffic up there. So what falls can be laying there for a while. So yeah, those are all good reasons. So another thing, and you can, I've thought about making this into a lab, but there are ways, if you read on the internet, to actually go out and find micrometeorites. We're like a meteorite. I want the meteorite, but they're actually little tiny pieces, pulverized pieces that fall to Earth from space. Earth picks up so many tons a day of just material falling through its atmosphere from space. Isn't that kind of creepy? Yeah. So this, good, bad, or otherwise, this is showing you this rock or meteorite fell through that car. Yep. They get famous names. There's different ways to kind of classify meteorites. One of the ways is listed here. These aren't listed here. This is part of, this one right here is kind of a primitive meteorite. The dating says that actually it says before the solar system. That's how old that one is. This one actually is an iron-looking one, iron meteorite. This C doesn't really glow. It's just got a slight source behind it to glow. All right. So we are knocking them out. Bless you. How many of these do you need to do? Oh, by the way, I kind of looked at, it's good here. I looked at, when I was getting ready to do the test, I originally said that the test might just kind of come from these that we didn't do, and they might a little bit, but there's not enough here. So I kind of did that idea. Well, let's start the next one. We won't get through it all. I know it's like a lot, but all right. Comets. What's the difference between a comet and an asteroid? I think, if you had to tell somebody about it. Where did I say comets are? They're over there. And so since they're over there, they're farther from the sun and it's colder. So since it's colder, no. Since it's colder, they can have actually ices. Ices was my point. They can have ice, like ICE, like ice cubes. Oh, next one. Okay. So comets, like asteroids, are kind of left over from the formation of our sun and the planets. We collectively call the sun and planets the solar system. Now, you guys told me what planets is the asteroid belt between? Mars and Jupiter, yep. And actually, as later on, we're going to call that kind of break the frost line. Like things freeze over here, away from the sun. Things here, close to the sun, they won't freeze. They won't solidify. Okay, this is the frost line. So, with all that in mind, if you're on this side of the frost line, like I said, you can have water would freeze. Over here, water wouldn't freeze. Okay. So over here, water can go ahead and deposit, be frozen on a rock we call a comet. Over here, that rock would just be an asteroid. That's it. So in order to talk about comets, in order to talk about comets, I have to go clear out here. And there's two regions clear out here, actually. They're listed here, the two regions. They're listed in order how close they are to the sun. So we have the Kuiper Belt, which is kind of in the starts letter E. What do I call this right here? The ecliptic. Very good. This is the ecliptic. The Kuiper Belt, kind of think of that as being in the plane of the ecliptic. Kind of. And so Pluto is out here. And think of Pluto as being kind of in the beginning of the Kuiper Belt. Okay? Kuiper Belt. KBO. Kuiper Belt objects. Pluto is just kind of a Kuiper Belt object. Actually, the reason Pluto got demoted or whatever is they found, and they called it Eros at first, they found another object here. This is Pluto. This is another object, Eros. Both orbiting the sun. Eros is even larger. And both Pluto and Eros are dwarf planets now. Okay? And both Pluto and Eros are icy, rocky objects. So they're basically glorified comets. We think of comets as that pretty kind of thing you saw a little bit ago. But comets are, when they're out here, not near the sun, they're just kind of chilling. Right? So comets. So we have the Kuiper Belt, and even farther from the Kuiper Belt, we have the Oort cloud. And doing Oort cloud, I kind of go back to the sun, and I kind of go like this. So there's the Oort cloud. It's really humongous. It's spherical, okay? So that's kind of where those icy, rocky leftovers ended up. The Kuiper Belt, or the Oort cloud. All right. So most comets go unnoticed by us here on Earth. This kind of talks about the demotion of Pluto. So finally, back in 2006, finally scientists got together to define what a planet is. They came up with 3 criteria for a planet. Let's see, I failed that criteria. 3 criteria for a planet is it needs to be spherical in shape. And being spherical means it has a certain mass. Because remember we saw, Vesta and Sirius. Those asteroids are spherical because they have enough mass. So that's not the only one. What was the second one? Oh, yeah. One is that the object has to orbit the sun. Duh, right? For a planet needs to orbit the sun, our star. But the third criteria was it needs to have cleared its orbit. So it orbits the sun, and if you look in its orbit, it needs to have cleared its path. In other words, if you go back to the snowball analogy, during kind of the whole, I'm going to pick up my stuff, kind of in my track that all the planets were doing while the sun was forming, it needed to go ahead and clear its track. And that's where Pluto fails. Because I already kind of told you out here in the Kuiper Belt, there's all sorts of crumblies, so it's not a clear path. So that's it. So, dwarf planets, Eris, Makemake, others. So dwarf planets. We'll talk more about Pluto, I think, later. Comets. So the only reason a comet looks visible, well, not the only, if you had a really good telescope, and I just thought of the Futurama, the sniffoscope, right? But if you have a really good telescope, you actually probably could, the only way you could see a comet that's out there in the Kuiper Belt would be the same way that you see an asteroid, which is light from the sun reflected off of it. So the way these guys get sent sunward actually is they get a little push or pull or nudge, oftentimes by a lot of different things. One is like a planet kind of reaches out its gravity. It can have another nearby star give it a nudge. So here's some pictures of some comets that are going towards the sun and glowing. Now they glow for a different reason than our meteors glow. I think this is a good place to stop. We'll pick up on the slide on Friday, equinox.